Okay. Problem 4. We have a periodic function with period t naught, and it's odd. And so this is an odd function. If f of t is odd, use a Fourier series analysis equation to determine the constraints on C0. So this was actually a homework problem. Okay, so C0, let's just write that out. Let's write it symmetric integrals about t equals 0. F of t dt. Okay. Now, there's an easy way and a hard way to do this. Let's do the easy way first. So let's think about what this means. F of t is odd. So let's draw an f of t. F of t is odd means if f does something for positive t, it has to do the opposite for negative t, right? So then if I imagine integrating over these symmetric limits, this part has to cancel out with this part, right? And so my integral must always be 0. That's the easy way. Now the hard way, maybe the more rigorous way, is to divide this up into two integrals. 1 over t naught, integral from minus t naught over 2 to t naught over 2, f of t this should be 0, f of t dt, plus the integral from 0 to t naught over 2, f of t dt. Okay. So why do I do this? Well, I can consider the positive and negative parts separately. Okay, so this second integral, I can make a substitution that t prime equals t minus t. Okay, so what I'm left with is c naught equals 1 over t naught, integral from minus t over 2 to 0. Actually, now I'm going to need to change these limits, so I can't write them in yet. Okay, t prime equals minus t, dt prime equals minus dt, and the limits have to change, right? So this has to become, this stays 0, this becomes t naught over 2. Okay, f of minus t prime times minus dt prime plus integral from 0 to t naught over 2 f of t dt. Which is equal to 1 over t naught. Now, what I'd like to do here is swap these limits because I want to make it look similar to the one on the right. Okay, so what I'd like to do here is swap these limits, and if I do that, I have to take a minus sign out here. That cancels with this minus sign, so that's going to give me a plus sign, f of minus t prime dt prime plus integral from 0 to t naught over 2 f of t dt. Okay, so now noting that, remember the odd function means f of minus t, and t prime are just dummy variables, right? So f of minus t is equal to minus f of t. Where are we? Down here. So these two cancel out, right? Because this is equal to minus f of t prime. So this is equal to 0. So we're done. Okay. Now the second part is write f of minus t by using the Fourier series expansion. Fourier series expansion. So that's easy. F of minus t is equal to the integral from n equals minus infinity to infinity, cn e to the j 2 pi n t over t naught, right? And because it's minus t, I have a minus t here. It's relatively painless. Okay, and so the next one says if f of t is odd, find the relationship between these Fourier series coefficients for n equals Cn and C minus n. Okay, so the way we do this, or at least the way we suggested we do this, is we use the fact that the function is odd. That implies that the Fourier series expansions also have a relationship. So that is the Fourier series expansion for f of t. So that is equal to minus the Fourier series expansion for f of minus t. Okay. And so if we want to match terms, and that's kind of what we generally do in these proofs, we can see here that this n equals, let's say n equals 1 term here is going to correspond to the n equals minus 1 term here, right? And n equals minus 1 term here would correspond to the n equals 1 term on the other side, right? And so the way we do this mathematically is we multiply by another complex exponential, let's say e to the minus j 2 pi m t over t naught. Divide by t naught, integrate over a period, and then we use orthogonality. Of course, I don't want to go through all the steps. If you at least use the word orthogonality, that's enough to get you full credit, which means you realize you can go through these steps. Okay, but in general, if we don't explicitly say that, we can't always match terms like this, particularly if we had some other function here that were not complex exponentials that where orthogonality didn't apply. So if these were like polynomials or something, you wouldn't necessarily be able to equate these two. Okay, so this is very specific to complex exponentials, and so we have to mention orthogonality. But if we do that, then we can just match terms. Okay, and so what that leads to is that C n is equal to minus C minus n.